Ladies and gentlemen, may we have your attention, please? The opening ceremony is going to start. Please be prepared. Om Swastiastu, Assalamualaikum warahmatullahi wabarakatuh, Shalom, Namo Buddhaya. Good morning to all of participants that join here in our meeting room and join via online, and also to our honorable speaker. May peace be upon all of us. It is an honor to me to introduce and welcome Professor Gerard from Amsterdam University Medical Center, the Vice Dean for Academic and Planning of Faculty of Medicine Universitas Udayana, Dr. Igede Eka Wiratnaya, Specialist Orthopedic Surgeon, the respected head of Clinical Pathology Residency Education Program, Faculty of Medicine Universitas Udayana, the respected head of Association of Clinical Pathology Specialists Denpasar Branch, the head of Indonesian Association for Clinical Chemistry, the respected staff, professor, and consultant of Clinical Pathology Residency Education Program, Faculty of Medicine, Universitas Udayana, as well as my beloved friend, all the resident doctor for clinical pathology who are joining this expert lecture event this morning. For a brief moment, we would like to invite you to rise and sing Indonesian anthem, Indonesia Raya. May all we rise. We are now going to listen to the opening remark delivered by Professor Dr. Ana Agung Wiradewi Lestari, Specialist of Clinical Pathology, as a representative of the Head of Clinical Pathology Residency Education Program, Faculty of Medicine, Universitas Udayana.
Ladies and gentlemen, good morning. First of all, I would like to express my praise and gratitude to Almighty God for the opportunity given to all of us so that we can gather and attend the guest lecture with topic hereditary disease in Indonesia and laboratory diagnosis, which will be presented by Professor Gerard from Amsterdam University Medical Center. Okay, thank you. And we will continue our meeting. The time is yours, Prof.
Okay. Inherited diseases in Indonesia, as in most of Southeast Asia, actually are a problem that's underestimated. There are many. Sorry? Oh. So, most of the attention in the medical world here has been on infectious diseases like COVID. I adjusted my opening slide a little bit with the face masks. In my country, in the Netherlands, we don't use the face masks anymore. except in contact with patients, of course, and in the trains and in the public transport in general. This is where I come from, VUR University Medical Center, joined forces with the Amsterdam University Medical Center. And this is my team at Prodia. It's a big company supporting hospitals everywhere. I will start with a very basic thing in genetics. And I like this lady from, I think it's Game of Thrones, but I liked her double-stranded hair and the other side single-stranded. It's like RNA and DNA. And the central dogma in molecular biology is DNA encodes RNA, encodes protein. But like all dogmas, this one is not true. There are also many genes that only encode RNA. So I hate dogmas. But some basic things about genes and the genome. We now talk a lot about the genome, genomic sequencing, etc. So the genome is all our DNA and the gene in the old definition was the information for one trait, and that's from the 19th century already. And nowadays we say it's the DNA code for a protein or an RNA molecule. Genome is the entire code of all chromosomes, and it consists of 3.2 billion base pairs, nucleotides. 1.5% is protein coding genes, but 4.5% is RNA coding genes. And for most of the RNA coding genes, we have no idea what they are doing. Two very big ones are the ones that encode the two building blocks of the ribosomes. There are around 25,000 protein coding genes, and when we started sequencing the human genome some 25 years ago, we thought we would find at least 100 to 200,000 genes based on the number of proteins that we knew, but it was only 25,000. But we didn't realize at that time that the step from DNA to messenger RNA has a phase called splicing, and that can be done in different manners. So one gene can encode many different proteins. At the bottom, you can see all the different proteins, and the antibodies are a huge number, so we can make more than 1 million different proteins with our genome. So challenges in genetic testing and of course, genetic diseases, the awareness. Inherited diseases, each of them is rare, but together 6% of any population has a genetic disease or a genetic susceptibility to disease. We know more than 8,000 inherited diseases now. And in the medical professions, most MDs in Southeast Asia don't know about inherited disorders, not enough at least. And the health insurance is a problem because genetic testing is about prevention, and prevention is not on the agenda of health insurance yet. So that's something also we need to work on, the awareness of that. Money. Indonesia has input regulations and taxes that are aimed at protection of the local economy, but it's disastrous if the local economy cannot produce the things that we need for genetic testing, for the hospitals. So I've been working on that, lobbying for the last 20 years about removal of those taxes. And in the research setting, we can now ask for exemption of tax. There's a big stack of forms, of course, because you perfect the bureaucracy to a level that's completely unbearable. But it's still possible to get a tax exemption now, but not in a hospital because that's not research. So we're talking about monogenetic diseases here, in inherited diseases. So we have to differentiate between diseases that are caused by a background of genetic susceptibility, so many common variants in many different genes. Diabetes is an example of that. Diseases that are caused by a single variant in a single gene, and we call those the monogenetic diseases. So you can do analysis of one specific gene if the symptoms are suspect for a specific gene, and then the method of choice is Sanger sequencing. I will not go into the specific details of all these methods here today, because each of the methods needs a full hour, I think, to explain. So Sanger sequencing is the method to sequence small parts of DNA copied by PCR, up to 600 nucleotides usually. And you can use that also when you have detected the mutation in a family by next generation sequencing. You can follow up in the family with a very cheap and simple PCR of the environment of the variant, and you can do that on Sanger sequencing. And the next generation sequencing made it possible to look at many genes at the same time. So we do panels of genes, like I showed you in the previous slides. For example, we have a panel for breast cancer, a panel for cancer susceptibility in general, a panel for cardiovascular diseases, connective tissue diseases, etc. So that's targeted next generation sequencing. You enrich the DNA of the patients for a specific gene panel. And then we have the whole exome or whole genome sequencing. If there are too many genes for a panel, or if the gene is unknown, we use the next generation sequencing to sequence all the exons in the entire genome. That's about 180,000 exons. And nowadays we tend to, instead of panel sequencing, we do whole exome sequencing in all patients, and then we, for the specific patient, we do panel analysis. So we have a panel on in silico in the analysis step. We only look at the genes that are related to the specific disease in that patient. That makes it much easier for the laboratory. You have only one workflow. Every patient will be sequenced, unless it's a family member, of course, but all the patients will be sequenced by whole exome sequencing. It's more expensive, but because you save a lot of labor, for us, it's more cost effective to do it this way. In Indonesia, it may be a bit different because of the price of the chemicals and the instruments and the consumables is twice as high as in our country. And labor is about 10% of the cost of in our country. So we have to look at that.
I think this is the end of our lecture this day.